This presentation will be about synchronous lateral excitation for the University of Wyoming Vista 1000 class with Professor Denzer, fall 2019.
So, what is SLE? This is essentially caused by pedestrians walking on a bridge. As a pedestrian walks, they create movement in three directions: vertical, lateral, and longitudinal. The lateral component of this force is what causes this phenomena, and that lateral component is caused by the sideways oscillation of the human center of mass as they walk. When you have a large crowd of people on a bridge, you experience a crowd loading, and the lateral vibrations can be amplified if the natural frequency of the footbridge is less than 1.3 hertz. So as this phenomena occurs, pedestrians will attempt to maintain balance, which ends up amplifying this phenomena. So pedestrians will walk with their feet further apart, therefore increasing the lateral force and lateral vibrations. They synchronize with the movement of the bridge in order to maintain balance, which increases the movement. This increased movement therefore leads to increased synchronization between the pedestrians walking with the bridge and with each other. This can increase the phenomena and cause problems like you see in this video here.
This video is of the London Millennium Bridge in London on its opening day. You can see in the video that the bridge is swaying side to side, and this is the lateral excitation.
So in this diagram, you kind of have a depiction of how the footsteps create this lateral movement, and a representation of how the lateral movement in the person of 1 hertz could sync up with the natural frequency of the bridge and cause that.
So how do engineers deal with synchronous lateral excitation? There are two main ways we can deal with SLE in designs. So you can start at the drawing board and you can build your bridges with appropriate frequencies. Those are usually above 1.3 hertz. So this ensures that the pedestrian walking won't end up syncing up with the bridge. And they also use tuned mass dampers. Tuned mass dampers will be described in the next slide, but they do not require a fixed point, and they can be incorporated in critical points along the bridge. They can also be viscous or solid mass based, which makes them very versatile. And like I said, they're used to control lateral vibrations, and they were also added to the London Millennium Footbridge to solve this problem. So this is an example of a tuned mass damper from Dicon Dynamics and Controls. So essentially, you have a vibrating mass. In this case, it's a very thick piece of rubber and springs, and they vibrate out of phase with the structure it's attached to, and this essentially eliminates the vibration in the structure.
This is just a list of all the sources we used for this presentation. They'll be available in the description if you'd like to learn more.
Thanks for watching.